Thank you very much. I'm really grateful to the organizers for inviting me here. It's a very interesting conference and beautiful city. I'm enjoying every moment of it. So now my talk is not quite like David's talk this morning, which 100% matched in the topic of the conference. Um, Perhaps one can present this as a discussion of so to say non-commutative spaces. So instead of homotopy groups, there will be semi-rings. Okay, so well, I'll start with recalling some general results which were known for maybe 2 decades already. And of course, there are experts in the field present here in this room. So I'm not trying to rediscover these results, but rather maybe interpret that in a somewhat new way. Okay, so let's recall something. So we start with a non-degenerate braided fusion category E. So David this morning explained what non-degeneracy means. It really means that the category as far from symmetric as possible. Now, what I'm going to say is probably very likely true for tensor categories that are not semi-simple, but let me just stick to that for safety, and we will work over complex numbers or any algebraically closed field of zero characteristics. So one known result is that, first of all, if you have a braided category, then you can tensor module categories over it. So you have this product, which usually denoted like that. So similarly to how one tensors modules over a commutative ring. And the Picard group is precisely, well, it's categorical group. It's the group of invertible bimodule categories. So a theorem of Wittengoff, Ostrich, and myself states that there is an equivalence between these categorical groups. So one is the group of invertible modules, that's the Picard group, and the other is the group of braided equivalences of B. Now, what's the point of this? The point is that it's kind of hard to tensor module categories explicitly. The tensor product is defined by universal property, and it's usually cumbersome to compute it. On the other hand, it's easy to compose at equivalence. So that was the main idea behind this. Now, let me explain how this isomorphism or equivalence of categorical groups is defined. So just think, for example, for modulo over a commutative ring. Then multiplication by an element of this commutative ring is an endomorphism of this module. Now, similarly, we can have a similar construction for a braided category, but there is some difference here, some novelty, namely we can use either braiding or its reverse to equip the functor of tensor multiplication with the bimodule structure. And if category is symmetric, then these two things coincide. And if it's non-degenerate, they're actually quite different. So what one does, one assigns to a module category M this composition over here. So one composes one of these functors. They're called they were called alpha induction by Bokenhauer, Evans, and Kawahiashi. And one composes one of these functors with the inverse of another. So think of this as a ratio difference of two functors. Okay, and turns out that this assignment that assigns to M this functor is precisely the equivalence in question. Now, I'd like to point that like these functors here, they make sense for any category M, invertible or not. Okay, now, of course, if it's not invertible, then you cannot take inverse. What you can do, you can take adjoint. Now, there is a important matrix associated to this called the modular invariance. And what one does, one takes here vector spaces that relate these two functors, the alpha plus functor and the alpha minus one functor, and computes the dimensions of the home spaces. It's a square matrix whose rows and columns are labeled by the simple objects of the category. This, it was known to physicists for, well, to scientists for quite a while. I learned it from the paper of Christoph Ingo and Fuchs. So where they describe this in detail, the point is that this matrix commutes with the action of the modular group, hence the name modular invariant. So Fuchs, Röpke, and Schweigert also showed that this is multiplicative, namely, well, they use the language of algebras, but translated to the language of module categories, it amounts to this being multiplicative with respect to the tensor product of module categories. So, for example, like if we start with invertible M, this ZM is just a permutation matrix because at equivalence naturally permutes the simple objects of the category, so you get this permutation matrix. Okay, so this all was known. Now, so let's see. I'd like to reconcile these two constructions, namely what we have at the moment. For invertible category, we get at equivalence. For a general category, we get a matrix. So clearly something is missing. Okay, so now, like I said, this functor Fm. So now instead of inverse, I am taking the adjoint. Okay, and that becomes an endofunctor of B, which is, in case of invertible M, is at equivalence. Again, this functor is well known, was considered in great detail in the paper by Froelich, Rünke, and Schweigert. And I think, well, again, to me it was a new observation, but it's quite possible that people realized it all along that this is in fact a braided lax tensor functor. So braided means that it commutes, that its tensor structure commutes with braiding, and lax means that the structure morphisms, namely maps between fx, fy, and fx tensor y, are not necessarily isomorphisms, but satisfy the same axioms that a tensor functor do. Okay, now it turns out that the composition of such functors is also monoidal, namely it commutes with the tensor product over B, and that this assignment that assigns to a the module category M this corresponding functor is in fact a monoidal functor. Okay, so here mod B is of course a two category, but we truncate it as like endofunctors form a one category. So in this sense, the modular invariant that we have seen on the previous slide right here is nothing but the graph. Well, graph maybe not the right word, but that's kind of like the multiplicity of the images of this functor on simple objects, and the commutativity property, and the multiplicative property of the M is a consequence of this multiplicativity property of the functor that assigns F to M. Any questions so far? All right, moving on. So, okay, well, we have this functor. One would like, in particular, to be able to characterize the image of this functor. In other words, to see which Lax braided functors appear in this way. And it would be also nice to interpret this equivalence between invertible B modules and braided anti-equivalences of B as a restriction of an equivalence between certain non-invertible things. Okay. So that's the agenda that I have. All right. So now, so we kind of introduced like two types of objects, right? Module categories and endofunctors. And turns out that there is a third kind of type of structures, namely the central étale algebras. So again, the notion of étale algebra, I don't think it was mentioned yet. Okay, so what étale algebra is, it's a commutative separable algebra in a braided category. Now, what this means is that when you take modules over this algebra, that category becomes a monoidal and rigid. Okay, first thanks to commutativity, second thanks to separability. Now, we start with the fusion category C, which may or may not be braided. And suppose, now its center is a braided category. And having such an algebra in the center allows you to produce this category, which I denoted rep CA, that's the category of A modules in C. So A being algebra in the C, in the center is particular an algebra in C, right? And one can do all these things that I mentioned, taking modules and so on. Now, this category is, since we started with the fusion category, this category is multi-fusion. And the free module functor is a tensor functor from C to this multi-fusion category, and this functor is dominant, or sometimes people say surjective. Now, there is also construction in the opposite direction, namely having such a tensor functor from C to a multi-fusion category, one can take its adjoint, an induction, and apply it to the unit object, and the result is an étale algebra in the center. So we have two directions, right? From tensor functors to étale algebras, and other way around. I think this was first observed by Bruguière and Natale maybe 15 or 20 years ago. So now let's see. Well, why is this relevant? It's more general than the theory of module categories, because what's a module category? Well, it's also a tensor functor from C to the tensor multi-fusion category of endofunctors, linear additive endofunctors of M. Right? So it's just like, like you have a module and the representation, the two equivalent notions. So again, one way to distinguish such module categories among all functors to multi-fusion categories is that the center of this NM is trivial. So, well, there is a theory here that tells you what the center of this category is. It's precisely the category of local modules in the center with respect to this algebra A. This is the result of Schaumburg. Now, again, this notion of a local module is quite central from what I'm going to talk about, but I don't think it was mentioned yet at this conference. So let me go over it. So we start with the braided category B and an étale algebra in there. It's a commutative algebra. We can take modules. They form a tensor category, but among such modules, there are really good ones. Okay, so those are modules whose module action row is stable under the squared braiding. Okay, so that's what is written here. So rho is the action of A on M, and applying the square of braiding to A tensor M is an endomorphism, and it doesn't affect the module action. So it turns out that local R modules form not just a tensor category, but in fact a braided category. All right. So now I should tell you, for people who have seen it, that's a standard construction. For those who have not or forgot about this, so here is a good analogy that should explain everything. So suppose you have a vector space with a quadratic, non-degenerate quadratic form, right? And suppose you have an isotropic subspace. So that would be a subspace where the quadratic form restricts trivially. Now, of course, we can take a quotient of the vector space by any subspace, but here is the thing, it will not inherit the quadratic form. What will inherit the quadratic form, which is a standard, of course, thing in linear algebra, is this quotient. So if it's an isotropic, then it's contained in its orthogonal complement, and this thing is a quadratic space, okay? So that's precisely this is precisely the linear algebra counterpart of this local module construction, okay? So I will be using this construction consistently. And in particular, we can introduce the notion of a Lagrangian algebra. So these are precisely an algebra in the center such that the category of local modules is trivial. Okay, so well, there are other ways to rephrase this property. Well, this is like kind of maximal étale subalgebra. Okay, so presence of such Lagrangian algebras actually characterizes the equivalences between given category and the center and centers of a fusion category. So now, comparing this to the previous slide, right, the dominant tensor functors correspond to étale algebras in the center. Then Lagrangian algebras, they are in bijection with indecomposable module categories. So this provides like the third type of language, right? So we have now like three. We have the language of tensor functors, the language of étale algebras, and like the endofunctors that we considered before. Questions at this point? Yeah.
Yeah. Sometimes the term Lagrangian is used to describe maximal symmetric subcategory. Is that the same notion?
Well, that's a special case of what I was saying. So, like a maximal Tanakian category would be the category of representations of a group. In this category, there is an algebra of functions on a group. Right? So, like having Tanakian subcategory gives you a Lagrangian algebra. It's not the other way around. There are Lagrangian algebras that do not come from Tanakian subcategories. Okay, so for the last couple of minutes, we were talking about categories that are fusion, but not necessarily braided. Now let's switch back to a non-degenerate braided category B. Now, in this case, the center has a particular, the center of B has a particularly simple description, namely, it's a tensor product, the Linz tensor product of B and the category B reversed, which is the category with the reverse braid. Okay. So now, so we are going to use this fact in an essential way. And so one thing that I'm going to do, I will define a very simple operation, which I term a convolution. So it is an operation so that takes binary operation that takes as an input an object in B tensor B reversed and convolutes like two objects in the middle, X and Y, by means of this, right? So you have this home space and the outside objects W and Z survive under this. So again, this is a new product, right? Because there is kind of a natural tensor product with which B is equipped from the beginning. This is a new thing. Now, similar way, and we can define the action of this, the Deligne square of B on B by means of that convolution. So these operations have all the necessary associativity properties, and they are helpful to state the next result. Okay, so there is a, maybe I should have it on the different slide. Yeah. Okay, so there is a bijection or even an equivalence between appropriate categories between the category of Italian algebras in B tensor B reversed and braided lax endofunctors of B. And the assignments are very easy. So having an algebra, an Italian algebra, convolution with this algebra is a braided endofunctor. Convolution in the sense of the previous thing. The opposite direction. We can talk about the graph of a function, similarly how one can talk about the graph of a function. So here the summation is given by all simple objects of a tensor category. Now, if you prefer, this can be stated as a certain, as an object representing a certain functor, but let's not beat around the bush. The right idiom? Sure. Anyways, so yeah, so this, I mean, quite direct constructions. So the way they are related is, the way the necessary properties are established is this, like multiplication of A corresponds to the tensor structure on the functor, and commutativity of A corresponds to the braided property. So it's more or less a direct translation. So like this diagram emphasizes this correspondence that I have. Now, this correspondence, as I mentioned, can be regarded as an equivalence of categories, and it has all necessary additive and multiplicative properties. Namely, under this, connected Italian algebras correspond to indecomposable functors. So, I mean, for such endofunctors, for two such endofunctors, the direct sum is again, their sum is again an endofunctor. And convolution of Italian algebras corresponds to composition of endofunctors. Again, this is not necessarily new. I think many people use this one way or another, but I find it convenient to bring all these things together. Okay, so now there is a parameterization of Italian algebras in any tensor product of braided categories. This is similar to classical statement in group theory called Boursa's lemma. I think it was mentioned in this conference earlier. So, right, so one looks for algebras in tensor product, and for this end, one has a pair of algebras like sitting in one and another factor, and a certain like partial autoequivalence related the two. So this is an autoequivalence between subcategories of local modules. So again, it's less complicated than I'm writing it here, and in fact, we will only need this for that's not, and we will only need for Lagrangian algebras and module categories. So right. So now one can relate this describe this construction quite explicitly. So construct from this data and Italian algebras, and respectively, in view of the previous correspondence, the braided endofunctor. So what's braided endofunctor? Now, how to think about such endofunctors? So good analogy for braided equivalences are isometries or orthogonal isomorphisms. Okay, so here a special case of a Lax braided endofunctor would be a partial isometry. So that isometry that relates just one part of a space with the other part of the target space. But again, like so, this formula over here produces quite the most general description of such an endofunctor. So there is a good heuristic explanation why such functors have to appear. Namely, if you have a non-degenerate braided fusion category, then any braided endofunctor of this category is necessarily an anti-equivalence. So this is a consequence of the general fact that functors between braided categories come from functors between their Müger centers. So and so this kind of limits the strong functors that can appear in this way and somehow motivates the appearance of Lax endofunctors. Okay. Any questions? All right. So this diagram summarizes like these three perspectives on the same phenomenon, namely a dominant tensor functors, étale algebras in the center, and Lax braided endofunctors of a non-degenerate braided fusion category B. So I did discuss all these maps. Now, it turns out that for practical purposes, this étale algebras in the center, they serve like an intermediary between these two things. So it's kind of a bit more complicated to go from here to here directly, but if you make it a transit through étale algebras, then the computations become easier.
What was E in the top one?
Whereas what?
What was D?
B is the original non-degenerate category.
D, delta.
D. Okay, so that's like, so you have the dominant functors from B to multi-fusion categories. That's what D is.
Okay.
Yeah.
D doesn't appear in the bottom one. I'm sort of one.
That's well. Well, it does not appear explicitly, but what appears on the bottom is constructed from this functor.
For example, these and the functors of a module category. It's module structure.
So again, like, good, thank you. So here is kind of like something which is perhaps easier. So we will only be interested in module categories, right? So here is the construction. So you start with a B module category, then form this endofunctor like in one of your papers, right? So well, this functor does use M, right? And that's an endofunctor of B. So that's how it is present. Okay. So now it is a somewhat non-trivial result to show that the composition of these arrows, that we go from the module categories to Lax braided endofunctors actually coincides with this functor that constructed from alpha induction. You have to identify two functors. Well, that's necessarily true. So now it should be mentioned, of course, that all these three categories, let's say, they are monoidal. So you can tensor the module categories. You can convolute Lagrangian algebras. And finally, you can, of course, compose the Lax braided endofunctors in a usual way. Now, so here I have this name Lagrangian because, the functors that appear in this way are rather special ones. And there are like several ways one can identify these functors, namely, again, I'll present two ways. hard to say which is better. So the simplest one is that such a functor preserves the Frobenius-Perron dimension of the regular object. Again, think about this as a certain isometry property, for example. There is perhaps a more conceptual way following the construction and discussion in the paper by Froelich, Fuchs, Runkel, and Schwager. So, namely, the Lax braided functor, although it's not like tensor, only Lax tensor, it does map algebra to an algebra, particular commutative algebra to commutative algebra. So this thing is an Italian algebra, the image of identity, and when you apply this Lax functor to an object X, it becomes a local module over this algebra. Now, such local modules generate a subcategory inside the set of all local modules, and that's, if it's the whole subcategory, then that's the type of a functor we need. It's Lagrange, we call it, just because it corresponds to Lagrangian algebras. Okay, so questions, comments. So, couple of years ago, Victor Ostrich asked me a question: what should be regarded as a Grothendieck ring of a fusion 2K? Now, there is a kind of naive answer to that, namely, well, it's a fusion category, so you tensor to think, you decompose them, right? So the result, some linear combination. Well, that's okay, but that's not, I imagine, the answer he wanted, because this way we lose too much, right? So we start with the 2 category, and we end up just with a ring, so we use 2 levels. If we only want to use just one level of information, then this one category that I was talking about of Lagrangian braided endofunctors is a suitable candidate for the notion of the Grothendieck ring of a fusion. Well, the only fusion 2 categories I'm going to consider are modules over non-degenerate braided fusion category B, but it's not really that far from the most general example in joint work with my co-authors, Peabody, Kappe, Houston, Johnson, Freyt, Pennis, Plavnik, Reuter, and you, we established that the study of fusion 2 categories reduces to the study of these modules over B and some group theory. Okay? So now, so what's the agenda here? Where can one go from this? Suppose you start with a braid. Now, it's a big mystery, of course, you know, the classification of braided fusion categories, like David this morning indicated that even, you know, the width classes are hard to describe, but, you know, let alone the equivalence classes. But here is a plan. So suppose you start with a category with a braided, non-degenerate, say, braided fusion category B, that you understand well, let's say a pointed category. And then if you construct an algebra, or monoid, whatever you call it, in this category, then this would produce a fusion category that could be viewed as an extension of this B. Now, think about the extension theory, which was mentioned by Colin in the previous talk, right? In this case, we construct sort of like a group algebra in mod B, and we use it to produce extension. But, you know, who knows? Maybe, you know, there are industrial constructions beyond group algebras, okay? And so there is like some kind of non-group theoretical theory of extension, okay? So that motivates, at least me, to try to understand better the underlying structure of the fusion 2 category of B-module categories, where B is not degenerate. Okay, so, well, there are a couple of things that we can say about that. Yeah, okay. So, as I discussed, and that now it comes very handy, that in decomposable bimodal categories are in bijection. They correspond to Lagrangian algebras in the center of B. And thanks to the Gursal lemma, now you can take a simpler version of that. This corresponds to triples A1, A2, and alpha, where A1, A2 are just two legs that this algebra has in the first and second factor respectively, and alpha is an equivalence relating local modules over these algebras. This was a fruitful approach in classification of module categories done by Kennedy Mitchell and Noah Snyder and Terry Gannon and other people as well, because it's a good parameterization and reduces module categories to algebras, which are easier to understand. Okay, now so let us use this parameterization and have two algebras corresponding, say, A1, A2 alpha, and then A1 prime, A2 prime alpha prime. Now, thanks to the fact that module categories over B are completely reducible, the result is a direct sum of some module categories, again, with different parameters, possibly with repetitions, but then it enjoys the following monotonic property. So the algebras that appear, so those that are with two primes, they are over algebras of A1 and A2. Okay? So which kind of introduces like a certain filtration on this category by a partially ordered set of this Italian algebras, kind of double filtration, right? One for the first leg, another for the second. That makes sense. All right. I can restate it a little bit, perhaps more conveniently. So one can try to organize, to order Lagrangian algebras by, Italian algebras, I'd say, in B, by the size of the localization, right? To every Italian algebra, you assign a localization, and then, some localization may happen to be equivalent, and some are not. So let's put all these algebras with the same localization, with equivalent localization in the same equivalence class. Make sense? So in this case, so I'm going to assign, denote it like this. So so right, so this is going to denote localization of B with respect to the first leg of this algebra, and localization with respect to the second leg is equivalent, right? Because that's what this alpha does. So I'm going to assign this. Then again, I can introduce a partial order on the set of Italian algebras, and again, with respect to this partial order, the multiplication is filtered by this partial order. Okay, so again, this is a feature of this particular ring, and also a monoidal category, right? So it's well, I don't think they were studied systematically yet. So this is our attempt to move in that direction. So so next, okay, and then of course, once you start doing something like this, you'd like to take the simplest non-trivial example and work it in as much detail as you can. So this is what we try to do with my graduate student Riley Chimber. So let us start with the representation category of the elementary abelian P group. So here P is prime, of course. Okay, now if you take the center of it, it's a really easy thing. It corresponds to a metric group or metric vectors, quadratic vector space, d-dimensional space over Fp, some with its dual, which has a standard symmetric bilinear or quadratic form. So now, from what we discussed above, so the business of describing multiplication there is really composing what is called Lagrangian correspondences. Now, well, I try to study literature quite a bit actually, but typically most of the results in Lagrangian correspondences you will find are in the setting of symplectic forms, that are useful in symplectic geometry. With orthogonals, not as much, at least, even in that case, I could not find anything remotely similar to an answer. So we proceeded to define these things, so to study these things ourselves. So we study Lagrangian correspondences in the appropriate quadratic vector space. And in view of the above filtration that I had, right? So remember, like we had the filtration by the size of the category of local modules. So here local modules are particularly easy. They're also going to be quadratic spaces, but of smaller dimension, right? And so there is a filtration by, so let's say we now talk about just a semi-ring. So there is a filtration by ideals, filtration by ideals, where each ideal consists of ideals LK consists of module categories, so Lagrangian algebras, where the dimensions of the legs of this A1 and A2 are at least k. Here k runs from 1 to d, where d is the number we start, the number of the dimension of the vector space. Okay, so all right. Now there are a couple of surprises that are, like, for me at least. So again, I don't know how to describe this ring or algebra as a whole. What we can do, what we were able to do though, is to describe this consecutive quotients. And well, the very first quotient is precisely what is spanned by invertible categories, and that's like the result I mentioned on the very first slide, namely it's the group ring of the orthogonal group of the standard 2D-dimensional vector space. It's more interesting when we go down. So for instance, the last idea here. So what is this precisely? So this would consist of Lagrangian algebras that are product, like Lagrangian algebra in the first factor, Lagrangian in the second. Okay, so it turns out that one can describe this in terms of associated geometry. Namely, so as a Z-module, it will be the endomorphisms of the free Z-module spanned by the basis consisting of Lagrangian algebras in Fp 2D-dimensional. But then the product, there is a standard construction in algebra. So if you have algebra or a ring, you can twist its product by introducing an element in the middle. Okay. Well, again, the name I'm familiar with this is called like sandwich algebra. And so here the sandwich element corresponds to, well, it's not quite the distance matrix, but it's rather, p to the distance matrix associated to a duopolar graph. So a duopolar graph is a well-known geometric thing. So it's vertices are Lagrangian subspaces, and adjacencies are those, so two such subspaces are adjacent if they intersect in the codimension one. Okay, so it's an interesting graph, and what is known, and it was quite a fun exercise to determine the spectrum of this matrix. And it turns out that it has a rather large zero space, so all but two, I think, eigenvalues are zeros. And in particular, this implies the following thing. So if you take the complexification of this ring, then the resultant algebra is not semi-simple. In fact, it's quite far from semi-simple because there are elements that are annihilating any other element, with respect to multiplication. So multiplication is very close to be like very degenerate in this case. So this was a surprise to me. I didn't expect to appear to witness an appearance of non-semi-simple algebras in this setting. And the other ideals are, well, like, okay, let me go back. So here, let's see, the first ideal is the group ring of the orthogonal group. The last one is a sandwich algebra. The things in the middle combine the two. So here you will have the smaller orthogonal groups of smaller spaces and like certain sandwich matrix rings. Again, that's my terminology, perhaps not the best one. Again, they all have a description in terms of certain geometric graphs associated to the isotropic Grassmannian. Okay, so these are interesting graphs. These are called distance regular graphs. There is a theory about them that helps a lot. Okay, so now that's as far as we are advanced there. Will be curious if this kind of algebra, like with this filtration and this this graded quotients is reminiscent of anything you have seen, because to me it looks completely new. Thank you for your attention.
Thank you very much for the nice talk. Time for questions.
This is